We ended the previous video with the electron configuration for neon, so 1s2, 2s2, 2p6. And I showed you how you could look at the periodic table and kind of run through these electron configurations. For example, this would be 1s1, 1s2, and then 2s2 would be here, and then we had 6, so 2p6 brings you all the way over to neon. And so for an electron configuration for an element in the third period, right, so this would be the first period, second period, third period. So let's do sodium. So sodium has 11 electrons, so one more than neon. But the second shell is full, right? So the second shell is completely full. So for sodium's 11th electron, we need to go into the third shell, into the third energy level. And so N is equal to 3 for the third shell. Possible values of L include 0, 1, and 2. So in the third shell, we're talking about an s orbital, right? One of them. P orbitals, right? 3 p orbitals. And when L is equal to 2, we're talking about a d orbital, right? And if you do your magnetic quantum number, you get 5 values for that. So we're talking about 5 d orbitals in the third shell, in the third energy level. And so if we plot those orbitals, right? So let's go ahead and plot those in terms of increasing energy. So this side we'll put increasing energy going this way, and the 3s orbital is here. And so that's what we're talking about. We're talking about the third shell. We're talking about the s orbital in the third shell, and there's one of them. Right. Next, we have 3 p orbitals, right, in the third shell. So let's go ahead and draw in those p orbitals, right? So there's 3 of them. So 1, 2, and 3. So those are our 3 p orbitals. And then finally, we have some d orbitals. We have 5 of them in the third shell. So 5 d orbitals. Let me go ahead and draw those in. So those are our higher energy. So 1, 2, 3, 4, and 5. So here are the 3 d orbitals, like that. All right, so let's do sodium. So let's go back to sodium down here. 11 electrons. All right, so we need so sodium has 11 electrons, and so the first 10, we could put the first 10 electrons in just like neon. 1s2, 2s2, 2p6. And remember, your superscripts tell you the total number of electrons. That's 2, 4, and then 10. So that takes care of 10 electrons. We have one more to account for. And so the 11th electron for sodium is going to go into the third shell, right? And the lowest energy here will be the 3s orbital. So we go ahead and put the 11th electron for sodium into the 3s orbital. So we can complete the electron configuration for sodium, and we have to add on 3s1 because we have 1 electron in an s orbital in the third shell. So the complete electron configuration for sodium becomes 1s2, 2s2, 2p6, and 3s1. Notice that all of this, 1s2, 2s2, 2p6, this is the same electron configuration as neon. And so we could represent all of that, right? We could represent all of this right here. We put neon in brackets, and then we could write 3s1, and this is another way to write an electron configuration for sodium. So we can call this noble gas notation because we're using the noble gas that precedes sodium. So if you just work backwards in the periodic table, right, if you go backwards from sodium, the first noble gas that you hit here is neon. And so we do neon's electron configuration. It's the same as neon's, and then we have to add on 3s1. So neon 3s1 is our noble gas notation for sodium. All right, let's just do another element in the third period. Let's just go all the way over here to aluminum. Right, so 13 electrons for aluminum. We can use noble gas notation to save us some time. So we're saying the electron configuration is the same as neon, and that puts us right here. Let me use a different color. Right, so that puts us right here. And then we have sodium. Right, sodium would be 3s1. Magnesium would be 3s2. And then let's go ahead and put those in. So magnesium would be 3s2, so we fill that in here. And then we need one more electron for aluminum, right? So we need one more electron, and of course that electron goes into one of these p orbitals here. And so let's go ahead and write the electron configuration. Just look at what we have on our orbital notation here. So we have 2 electrons in the 3s orbital, so 3s2. and 1 electron in one of the 3p orbitals. So we write 3p1. So brackets neon, 3s2, 3p1 is the electron configuration for aluminum. Let's go ahead and let's jump all the way over to argon here. So let's go all the way over to argon. So let's write the electron configuration for argon using noble gas notation. The noble gas before argon is neon, right? So we put neon in brackets. And then once again, we can think this is 3s1. We can think this is 3s2, right? So we have 3s2. We go over here. This is 3p1. 3p2, 3p3, 3p4, 3p5, and 3p6, right? So we can go ahead and write 3s2, 3p6 here for argon. And if we wanted to put in those electrons, right, and how they fill, right, we could put in those electrons, right, following Hund's rule, we talked about in the last video, right, and then we put in all of those electrons, and we can see that we've now filled the 3p orbitals like that. So that's argon. Next up is potassium. So now we're at the 4th period on the periodic table, right? So if we go one more element here, we hit the 4th period of the periodic table and we get to potassium. All right, so you might think, all right, so one more electron than argon. So you might think potassium's electron would go into a d orbital, right? Because that makes sense. We have this d orbital here, but that's not what happens. So let's go ahead and take that electron out of that d orbital. We are now, right, we're in the 4th period, and we can actually open up a new shell here. So we can go to n is equal to 4. We can go to n is equal to 4. Let me go ahead and write this down. And in the 4th shell, right, I won't write in all of the values for L, right, but we definitely have an s orbital. So there's an s orbital in the 4th energy level, right, one of them. And it turns out the energy for that 4s orbital is a tiny bit lower than the 3d orbitals. So let me draw that in with a different color here. So the 4s orbital turns out to be a little bit lower in energy. Let me use a different blue so we don't confuse it here. So this is representing our 4s orbital. So for potassium, the 4s orbital is a little bit lower in energy, so the next electron that we add for potassium is going to go into this 4s orbital. So we can go ahead and write the electron configuration for potassium. If we're using noble gas notation, we go backwards. So what's the noble gas that precedes potassium, right? So just go backwards in the periodic table, and that is, of course, argon. That's argon right here. So we could say that the electron configuration for potassium is the same as argon's, and then we have one more electron to worry about here. That extra electron, that 19th electron for potassium, is going to go into this 4s orbital here. So we write the same electron configuration as argon, and then we write 4s and one electron in that 4s orbital, so we write 4s1. For potassium, right, one more electron. So we can go ahead and write, for calcium, I should say. So for calcium, one more electron to worry about. So the noble gas that precedes calcium is once again argon. So we say it's the same electron configuration as argon. One more electron, and we know that there's space in our 4s orbital here. So we can add another electron, pair our spins up, and so we can say 4s2 here for the electron configuration for calcium. Once again, right, we notice this pattern on the periodic table. Right, so this right here, let me use blue here. So we could say this is 4s1, we could say this is 4s2, and so all of these over here on the left, we've just thought about them as being s orbitals anyway. So this is the s block on the periodic table. All right, that takes care of calcium, and the next ones that you're going to hit, right, are all of these elements in here. So all of these elements, and we know that in the 3rd energy level, right, there are d orbitals, right? So let's go back up to here. Let me go ahead and mark this so we can see. We know there are 5 d orbitals in the 3rd energy level. All right, each d orbital can hold a maximum of 2 electrons, so 5 times 2 is 10. So how many spots do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have these 10 spots here. right? And I'm actually going to do a whole separate video on the d orbitals, so I'm not going to worry about them in great detail right now. But we have 10 spots, right? And this is the third shell, and we have 10 spots for electrons. So 3d10 would fill these d orbitals. So 3d10 fills these d orbitals here. And this is why the periodic table is shown the way it is here. It just helps you to think about writing your electron configurations. For example, let's just go ahead to gallium here. Let's write an electron configuration for gallium. So if we're using noble gas notation, the noble gas that precedes gallium, if you work backwards, would be argon. So we can go ahead and write that in here. That takes us to this area. So that would be 4s1, 4s2. So we write 4s2 right here. And then we have all of our D's. So we can just go ahead and put the D's in there, 3d10. So we put in 3d10 here. And this takes us to we're in the fourth shell here, and it's equal to 4. So L is equal to 1 is another possibility, and so those are the p orbitals. So once again, we have 3 p orbitals in the fourth shell. And of course, right here, this is where we hit the p orbitals. We start to fill the p orbitals. So we can go ahead and say this is a p orbital in the fourth energy level, right? So a p orbital in the fourth shell, and we have 1 electron, so we can write 4p1. And so this is one way to represent the electron configuration for gallium, so using noble gas notation. So argon, 4s2, 3d10, 4p1. Sometimes you might see the 3d10 and the 4s switched in terms of their order. So you might see 3d10, 4s2, 4p1. And it doesn't really matter how you do it. You'll see both ways done. All right, finally let's do krypton here. So let's do krypton. All right, so our last electron configuration here. So the preceding noble gas would be argon. Right, and let me use a color that we can see here. So argon would take us to here, and then we have 4s2, so we fill 4s2, and then we have all of our d orbitals here, so 3d10, so 3d10 takes us to here. Now we're in the fourth shell and the p orbitals, so 1, 2, 3, 4, 5, and then 6. So 4s2, 3d10, 4p6 would be one way to represent the electron configuration for krypton. And once again, you could switch the 3d10 and the 4s2 if you wanted to. You could say for krypton, the electron configuration, the noble gas notation would be argon, 3d10, 4s2, 4p6. So just do whichever way your professor wants you to do it. So that's covering the third and the fourth period, but we've ignored the d orbitals. Again, that'll be a whole separate video because it gets a little bit complicated when you get into d orbitals.